just copying things like the objective down. Limits of an infinite sequence.
Can I go
No, not now.
class?
No, Miss Ecker, you must prepare for class, okay? I spent all this time preparing this for you.
Thank you.
And you could, if you wanted to, because I don't want to cut down too many trees. You can print this up.
Wait, what?
Let's look at the sequence defined explicitly as t squared equals a half to the n. I think you're familiar with this one, right? You keep cutting things in half. A half, so the first term is a half to the first. That's a half. The second term is a half to the second. The third term, a half to the third, so you get an eighth. The fourth term,
16.
there you go. And the sixth term is 1/64. Where are these going? As n gets huge, as n approaches infinity, the terms of this sequence get very small and approach zero. We call this the limit. The limit of 1/2 to the n as n approaches infinity is denoted like this. LIM. That's our abbreviation for limit. And then underneath the limit symbol, you write down what's going on with the index. The index n is approaching infinity. The limit as n approaches infinity of, now here, we put the nth term of the sequence, in this case 1/2 to the n. The limit as n goes to infinity of 1/2 to the n is, the limit is denoted as that, and it's equal to 0, as we said before. Just getting used to the notation at this point, and this is a big part of what we do in calculus. Because the whole point of calculus is to take the simple ideas from algebra 1, which is the slope between 2 points, and try and figure out how we're going to get the slope through a point on a function. Now that's kind of hard because if you do rise over n, you get 0 over 0. So we have to look at the limit process to see what it's approaching as it gets closer and closer to 0. We start actually with limits as n approaches infinity, because you can think of the limit as where is the sequence going. Okay? Okay, I think she can take her own notes. So just write it here. Here we go. A limit is something that terms in an infinite sequence are getting closer and closer to. But there's more to the concept. What's this limit? 1 plus a half to the n. The first term is 1 1/2. 1.5. And then the second term is 1 plus a fourth. 1.25. And the third term is
1.16.
1 plus an eighth. 1.125. And the fourth term, 1 plus a 16th. 1.06.
25.
And what does that limit look like?
1.
1. But hold it, wait. Why can't I say 0?
It's approaching 1. It's approaching 1.
But by this definition, all these are getting closer to 0. Nish, focus.
The n term is...
Maddie?
Because you have like the 1 plus 1.
So, are these not getting closer to 0?
Yes, they are.
This is closer to 0 than this one is.
But it's closer to 1 than it's closer to 0.
But it'll never be under 1.
Exactly.
So, there's something wrong with this definition then. We can't just say something that all the terms are getting closer to. Because all these terms are also getting closer to negative 38.29. Are they not?
Maybe it's getting closer to the...
So just saying getting closer and closer to isn't good enough. Yeah?
It's the greatest term that they're all...
But what if I come from underneath then?
Approaching.
Then you're going to change the definition to the least term? And what if I come from both sides and you're going to see which one are the limits?
You're talking about the average then, maybe?
No, we just have to add one little word. The fine-tuned definition. The limit of an infinite sequence is the number that the terms of the sequence are getting arbitrarily close to as n gets to infinity. So if some arbiter comes along and says you have to get within a millionth, I can't get within a millionth of 0 with this sequence, right? I can get within a millionth of 1. And this is going to be part of what we're going to look into in great detail in our section on limits, which is our last chapter of the year on limits and derivative. How you prove this is through, for any arbitrary gap, distance, error. This?
Can you just say that it's getting close, but it's getting closer to that constant term? Like, or no?
Well, I could say that as well here. 0 is a constant. Negative 42 is a constant. And all these terms are getting closer to that. It's just that you don't like it because the closeness never gets more than like 42 away.
No, the constant
It's
is
less than 42 away.
The constant is arbitrary. Because the constant can be anything, but once it's stated.
No, the constant isn't arbitrary. If I declare a limit, then it's not arbitrary.
No. But the constant itself, I know what a constant stays the same, but the constant can be anything, therefore it's arbitrary. Once it's stated, it stays a constant.
No. What if I said the limit here was 0.001? These terms are all getting closer to that, right?
Yes.
But then after a certain point, we'll get below 0.01.
No.
And then it'll start getting actually further away from 0.01.
No, it won't happen.
And the whole point is, once you pick some sort of arbitrary error, you have to get within that error and stay within that for the rest of the sequence.
That's a limit.
And that's the limit. So here the limit is 1. And we can pick for our arbitrary error 0.1. And at this point you say, oh, I'm not within 0.1 of 1 here, I'm at 1.5. Not here either. But now suddenly I'm within 0.1 of 1, right? And I'll stay within 0.1 of 1 forever after that point. So now some arbitrator can come along and pick any arbitrary positive number, and you have to get that close. So someone could say, we'll get within a millionth. As long as you go further enough out in the sequence, you will get within that millionth.
How do you make it stay? Because your numbers are going to change, your n is going to change, so how do you make it stay? What's in that limit?
How do I make it stay within that? Well, for this particular sequence, the limit is 1. And no matter what I pick for a closeness factor, like a billionth, you'll be able to find some point on the sequence, way further down the sequence, where it gets within a billionth of 1. Okay? Now I know what you exactly mean by how do you make it stay. What are you trying to make stay? The limit is a value. I think you all have an intuitive idea what the limit is, what it seems to be closer to. I just wanted to make sure you understand that it has to get within any arbitrary closeness.
Well, no, but how would you do it for like t of like 16 log is less than 1, so you pass your limit?
No, t of 16 won't be less than 1. T of 16 will be 1 over 1 plus 2 to the 16. It'll be just a little bigger than 1.
Okay.
Okay?
Oh, you can add.
Now, we're going to do a lot more with formal proofs of limits in that last chapter. For right now, you're just going to be required to analyze limits. And you can look at them graphically, and we also have a lot of limit tricks for figuring out limits quickly. Like, let's look at this limit. 1 plus negative 1 to the n divided by n. So the first term is 1 plus negative 1 to the 1 over 1. So that is just plain old 0. Second term, 1 plus negative 1 squared over 2. So that's 1 and a half. Third term, 1 plus negative 1 cubed over 3. So that's 2/3, because now we're going back to being negative.
Well, the first one shouldn't it be 1? Because 1.
Thank you. Yeah, I was just looking at that. No, negative 1 to the first is negative 1. No, it's 0.
1 plus it. No,
It's 0.
1 plus negative 1 is 0.
It's negative, yeah. Okay. So we get 1 plus negative 1 to the 4th over 4, so that's 1 and a quarter. So do you see a pattern here?
It's going up.
It's going up, but
Wait, so what the limit be 1?
Let's look at it in terms of a sketch here. Here's n and here's t sub n.
No, it'd be 4.
We start off at 0. Oh, here at 1 we're at 0. The second term was 1 and a half. And then the third term was 2/3. And then the fourth term was 1 and a quarter. And the fifth term will be 4/5. And the sixth term will be 1 and a sixth. Because of this alternating idea here, this is what I was talking about before. We're approaching a limit of what? 1. From both directions. So here's your 1. And you keep alternating from being above it and below it because of this negative 1 to the n we put in here. If it was just 1 plus 1 over n, then we'd approach 1 from above. And you'd see that 1 over n was getting closer to 0, and you're getting closer to 1 for the whole thing. So the limit as n goes to infinity of 1 plus negative 1 to the n over n equals 1. So you're approaching from above and below, but we're getting arbitrarily close. To get within a millionth, we'll just have to go to the millionth term, the millionth and first term. And then we'll be within a millionth of 1.
You don't really have an algebraic way to solve that. I mean, you can tell just by looking at it, sort of, but is there a...
Yeah, I'm going to give you some algebraic tricks. Because you don't have to do this every time you have a limit, is generate a bunch of terms and see what they're getting close to, but it certainly is a good idea. Especially when you set this up on a spreadsheet or look at some values on your calculator. We have some tricks for doing these limits. And here's an example of where, let's just try this on the calculator. Okay. The limit as n goes to infinity of the sine of 1 over n. I think I have, let's look at a couple of approaches on this. First of all, with no degree symbols here, this is in radians. And I think you can think about this conceptually because your terms are going to be the sine of 1, the sine of 1/2, the sine of 1/3, the sine of 1/4. And you can try those on your calculator. You can also remember the unit circle. Remember that old unit circle?
Yeah.
You start off here with that's 1. That's 1 radian. Here's half a radian, right? Here's a third of a radian. It's in radians now. Here's a fourth of a radian. And here's the sine of all these, right? The sine is how high. And where are they heading? They're heading towards 0. Okay. So there you go. Your limit is 0. You can actually do limit on your calculator under the calc menu again. F3 calc.
What order do the arguments go in now?
Did you try that? F3 calc, let's try that. And it says LIM, right?
And that says limit.
Now, you've got to put in the rule, in this case, 1 divided by n. You've got to tell us the variable that's changing. N. Thank you. Sine of 1 divided by n, n going to
But you can't put F.
infinity. There's an infinity symbol on your calculator.
Where's it? I don't. Oh, okay, here.
Does it like it?
Infinity is really cute.
Does it say 0?
Right there.
It's limit. It says limit.
Where's infinity? That's cute.
That is.
It's on there, people.
Star
Look around.
Star catalog. It's
You know how to go to catalog for infinity. It's right there.
No. I didn't press star on the catalog.
Oh, I see, right. It's above catalog. And it says 0, right?
Infinity is so cute.
Now let's do this by hand. Here's the trick to do it by hand. The limit as n goes to infinity of the sine of 1 over n will be the sine of the limit as n goes to infinity of 1 over n. If we have a composition of functions, we can look to see what is the change in n doing to the inside of the function. And this limit is what? As n goes to infinity of 1 over n. 1, a half, a third, a fourth, a fifth, a sixth, where is that going? To 0. So we can think of it the sine of 0. The sine of 0 is 0. So I'm starting to introduce ways you could analyze this without having to get out your calculator or hand do a bunch of terms. Let's try this on the next one. This one might help on the calculator too because I'm not familiar with my powers of 0.99. We can see what they look like. 0.99 to the first. I've got the first one. How about 0.99 squared?
I'm gonna have to ballpark it to 0.98.
Yeah.
0.9801. Is that right? Yeah.
Like
No.
that?
No. There you go.
0.9801, okay.
This is all mental.
How about 0.99 to the third?
0.97 probably.
Oh, hey, let's hustle things up. Let's do 0.99 to the 999.
Ooh.
We'll Everyone handle that?
Point. I'm gonna lower mark and say
How many zeros? 4 zeros?
6 1.
Okay, so now are you convinced what this limit is?
0.
Zero, but it actually gets there a lot slower, doesn't it? Than something like 1 over n or 1 over n squared. But, since it's a little less than 1, that's why we're going to come up with
But
a
how
rule
do you
now.
know the limit isn't 0.00000001?
I'm going to give you a rule. I'm going to give you a little handy-dandy formula, okay? Here it is. A little theorem. If absolute value of r is less than 1, then the limit as n goes to infinity of r to the n equals 0. Jot that down. That comes in handy. Because basically, this is part of our own arithmetic idea, right? R to the n. It's a very simplified t sub 1 times r to the n minus 1 formula. It's just r to the n. It's a geometric sequence. And the geometric sequence will grow if your common ratio is greater than 1. But if it's between negative 1 and 1, the geometric sequence shrinks and approaches 0. So this is handy for our geometric sequences and so forth. And we're going to see this condition a lot if the absolute value of r is less than 1. Because in our next section, you want to see if something is converging or not. Okay? So let's try these without a calculator now. The limit as n goes to infinity of n squared plus 1 over 2n squared minus 3n. Let me give you another limit too. The limit as n goes to infinity of 1 over n, we just talked about that equaling 0, right? That's a little different than this, isn't it? If you take a fraction between negative 1 and 1 and raise it to the nth power, that thing will approach 0. But now if I have a number like this, 1 over n, that will be 0. And that's not quite the same as this picture, is it? And in fact, the limit as n goes to infinity of 1 over n to the p power will equal 0 as long as that p power is greater than 0. Because you might say, oh, what if I'm doing the 1 over the square root of that? Those don't grow so fast, but they are still growing, right? As n goes to infinity, the square root of n will still get huge, and you'll divide by something huge. Okay? So keep that in mind then. So that's what we try to do on something like this. We change this limit into, and we multiply by 1 over n squared over 1 over n squared. It's kind of like the antithesis of all that work we did with least common denominators used to get rid of secondary fractions. We actually want to create secondary fractions in here. So this becomes the limit as n goes to infinity of 1 plus 1 over n squared all over 2 minus 3 over n. Now there's an advantage to looking at it that way. What?
It's not easy to substitute. Is it?
Take the limit of each part. Feel it? 0 through over n. That'll be 0 too, and you'll just left with these constant terms. That's the point of doing that little trick. You get the limit as n goes to infinity of 1 plus the limit as n goes to infinity of 1 over n squared all over the limit as n goes to infinity of 2 minus the limit as n goes to infinity of 3 over n. Okay? Now, this sometimes confuses students because they think, oh, it's 1, it's not changing. That's right, it's constant. It's unaffected by n changing. So the limit of this is just 1. What does that sequence look like here? There's a 1, and then there's another 1, and then another 1, and another 1, and another 1. It's just a constant sequence, so it has its limit of 1. Are we getting arbitrarily close? Yeah, we're always going to be at 1. So no matter what somebody says, can you get within a millionth of 1? Yes, we're there already. Okay. So 1 plus, this is what Julian's talking about now. This limit's 0, all over 2 minus 0, and we get a half.
But so the limit is 1/2?
The limit is 1/2. Now, of course, we talked about a shortcut for this earlier, and we'll review that again. But I want you to know the theory behind how can I break down and analyze the limit of something that looks new. Well, you can distribute the limit idea over division and addition and multiplication and subtraction. And take the limit of each part. But if I do that right away, I'm going to get the limit as n goes to infinity of n squared. What's that? The limit as n goes to infinity of n squared. That's going to be infinity. It doesn't really converge to a limit. Okay. Let's take a look at this one. Again, we want to use a little trick. Multiply by what? 1 over n cubed. To get as many constant terms as we can.
Can you put the square root of n to the bottom?
No, not to the bottom. Maybe if it was a negative power, I couldn't. I'd read it. If this was n to the negative 3, I'd write it as 1 over n cubed up here.
No, but then you could
This
write
n to the 1/2.
You could write 1 over n to the 4th.
No, you could not.
Oh.
Don't do that. Square root of n is not 1 over n squared.
No.
It's n to the 1/2 power.
No, it's just 1 over n.
No, it's not 1 over n. Square root of n is n to the 1/2 power.
Okay. N to the negative.
So we got 5 over n plus the square root of n over n cubed is 1 over n to the 2.5. Because we get a half power here and we're divided by 3 powers there. All over 3 plus 7 over n cubed. And then we take the limit of each part, and they're all 0. Even this n to the 2.5, because that's a power greater than 1. Right, greater than 0, actually. So it's going to eventually reach.
It has a 2.5. Square root of n times 1 over n.
Square root of n is n to the 0.5 power. N to the 0.5. Let me put a little step in here, okay? So now we get a power, now we get a limit of 0. Because the bottom is growing faster than the top. What, you don't believe me on this?
I don't understand how
Okay.
n the square root of n times 1 over n.
Yeah, let me show you. Limit as n goes to infinity of 5n squared over n cubed plus square root of n over n cubed all over 3 plus 7 over n cubed. This is n to the 1/2 power, so you subtract their 2 powers, and you get n to the negative 2.5, or 1 over n to the 2.5. I picked the biggest power in all the different terms. That's what we use to judge this. Notice what's distinctly different about these two problems. Look at the power on the bottom. It's bigger than anything on the top, so the whole fraction is going to get closer to 0. But here, we had equal powers on the top and bottom. So there wasn't a struggle. And it's almost like these terms became insignificant and you got n squared over 2n squared, or 1/2.
What if you had n squared over n? Yeah, what if it was bigger? Oh.
That's our next problem.
Oh, yeah.
You are psychic. Yes.
So, for limit problems, if there's over n in any case, it's just a 0.
Yeah.
If it's a 1 over n to any power, as I said here, it's equal to 0. Because basically the bottom is growing. As long as you put a positive power on n, it's going to keep getting bigger as n goes to infinity. And the 1 is constant, is fixed.
So if it's n over n.
So you're dividing 1 by something that gets bigger and bigger, that'll make the whole
But
fraction
what
approach
if
0.
it's like, it's like negative
Even if it's
1,
like
just
0.01, you just have to go far enough on infinity and it'll get smaller and smaller.
So if it's n over n, then it's like.
No, who said anything about n over n? Not there.
Again.
Yeah, if the degrees are the same, that's we looked at in this case. Now, sequences that have limits are called convergent. These are examples that we just saw. These are convergent sequences because they converge on a limit. They get closer and closer, arbitrarily close to a limit. If a sequence does not have a limit, we call it divergent. And here's our example. A half, 1 goes to, here's 1, to negative 1. 1 goes to a half, negative 2/3, 3/4, negative 4/5, 5/6. It looks like it has 2 limits. that the positive sections are getting closer to 1, the negative sections are getting closer to negative 1, but you're diverging and approaching two different limits. So diverging doesn't necessarily mean infinity, like the t sub n equals n squared. That diverges, right? So that's going to approach positive infinity. You can have limits like this, where you're heading toward two different limits. So you can't say the limit is 1. Because even though every other term is getting closer and closer, arbitrarily close to 1, the other ones are getting further than 1. Find these infinite limits. The limit as n goes to infinity of 4n minus 1. Well, that's, the first term is 3. The second term is 7. The third term is 11. Yeah, so this is approaching infinity. This diverges. And you might just have to decide which infinity on these infinite limits. Okay, just because the limit approaches, just because n is approaching infinity doesn't mean the limit has to approach something and converge. These diverge. So now here with negative 10 to the 1, remember this is negative 10. Negative 10 squared?
Negative infinity.
What's negative 10 squared though? Negative 100. The squaring happens first and then the opposite multiplier. Negative 10 cubed is negative 1,000. So Joey's absolutely right. This is negative infinity for this one. Okay? What if I put negative 10 quantity to the end? Yeah, but then it's also it's diverging. See, and this isn't really considered limit. We're just taking what the process is going toward, what's it heading toward. Now, show that this approaches infinity.
But I don't get the shortcut. Like there is no.
Why would you need a shortcut?
Well, this one because it's not really fitting the. This one you do have to kind of explore by looking at some numbers, because it doesn't really fit the pattern of the rules we talked about earlier, like 1 over n or r to the n if r is between negative 1 and 1. This one doesn't really fit the rules either, because when we multiply through by 1 over n cubed, should we? Limit as n goes to infinity of 7n cubed over 4n squared minus 5. Let's multiply by 1 over n cubed. So we get 7 over 4 over n minus 5 over n cubed. And so that's kind of hard to tell, because now we got 7 over 0 minus 0. 7 over 0. What is that supposed to be?
Undefined.
Well, it's not technically undefined because you're never going to get these to be 0. There'll always be something really close to 0. We're never actually at 0. So we never do get to division by 0.
It's not 1.
Well, it's going to be infinity because the top is growing faster. Let's try another tack on this. What if we do this? The limit as n goes to infinity of 7n cubed over 4n squared minus 5. Because this was giving us trouble with division by 0, let's multiply by just 1 over n squared. Now you have the limit as n goes to infinity of 7n over 4 minus 5 over n squared. And that'll equal 7n over 4. No, because remember, n is going to infinity, so that's where we get infinity.
Oh, because the n's not at the bottom. Would that be negative n? That's bottom.
Well, definitely the bottom is approaching just a constant 4,
Yeah.
but the top is still changing and growing. So if the bottom stays constant and the top keeps growing, then you're not going to converge anything. Now, this is best up by looking at the pattern we looked at before with rational functions. Remember rational functions? Well, I'm going to look at rational sequences. If the degree of P of n is what compared to the degree of Q of n?
If the degree of P of n is greater than the degree of Q of n, that's less than.
But in this case, in this example,
Oh, no, less than because the.
if it's less than,
Well, I thought we were writing the theorems.
oh, we're doing all three.
Yeah, I didn't see.
If the degree of P of n is less than the degree of Q of n, and you're doing this limit, then the bottom grows faster than the top, and you always approach 0. Okay? All right? Does that make sense? I mean, it kind of gets back to the idea of that limit as n goes to infinity of 1 over n. We said, hey, the bottom is growing, the So that's why we said the limit was 0. Well, now you can judge which part is growing faster. So it's not based on the coefficients. It's based on the actual degrees of both these polynomials. So this has higher degree. Now, if the degree of P of n is equal to,
Then it's an arbitrary.
then the limit is the ratio of the leading coefficients. And we proved that with one problem, but now let's just jump to this conclusion
7
here.
divided by 4.
So this is 7/4. Now we go through the proof again. Multiply top line by 1 over n to the 4th. Then you get 7 over 4 plus these other terms that go to 0. I'm not going to expect you to prove that every time now, but you can just go right to this idea. You recognize it as same degree over same degree, so you can look at the ratio of the leading coefficients. Okay? Okay? Okay. That's 2 cases so far. What's left?
The top is bottom, the bigger.
If the degree of P of n is greater. Right. Here we got the 5th degree or the 4th degree, so the whole thing approaches infinity. Well, in this case, we're picking infinity because the leading coefficients are both positive. If one of them were negative, one was positive, then the whole thing would approach infinity. The way to judge this easily is look at your leading terms. So this is going to get closer to the limit as n goes to infinity of 7n to the 5th over 4n to the 4th, or the limit as n goes to infinity of 7n over 4. And that's basically a line. It's going to act like a line with a positive slope. So as n goes to infinity, we approach that. So that's my question. Give an example of a sequence whose limit is negative infinity. How can we have that happen?
Negative 7
over
positive 4.
The limit as n goes to infinity, negative 7n to the 5th plus 5n over 4n to the 4th plus 42. That would be negative infinity. Or how about the one Joey had before?
Negative 10.
Written like that, right? Okay. This class actually ends at 1:35, so you got some time to check out the talk board, show me what you got, ask any questions. Let's save this.